Math 287, Cuesta College. I'm Joe Vasta, and this is section 5.3, the Gram-Schmidt process. So I have two vectors, A and B. I'd like to know what B minus A is. Now some of you might remember, oh yeah, it's a triangle. It completes that triangle, but which way is it pointing? Up to the left or down to the right? Well, to figure that out, you could just say we have a negative A here, and that would take vector A and make it point this direction. Now I'm going to kind of go off the slide there. And then I'm going to add the negative A plus the B using a parallelogram, and so that vector, negative A plus B, or B minus A, is going to go up to the left. And so that's what it is. And so we need to know how to do this for our derivation of part of the Gram-Schmidt process, whatever that is. So I have those two vectors, A and B, and now what I want to know is the projection of B onto A. Well, what is that even? What you do is you put A and B together, put their tails together, and then draw a perpendicular line down or up, and in this case it's down to A from the tip of B. So I have that. What the projection of B onto A is that red vector going from the tail of A to where the perpendicular comes down. And somehow I want to write an expression for that red vector. This is very theoretical. It might make some of you feel uncomfortable, so you can skip ahead in the video if you don't want to see this derivation. But here it goes. What is the length of that red arrow? Well, we don't know. But when you don't know something in math, you look 10 times smarter if you just label it X. Look, now I know it's called X. Okay. Notice there is a right triangle there. I'm going to reproduce that right triangle off to the right. And I put length B right there, because that's the length of the hypotenuse. We have A. Well, that's not A, that's an X. And then I think I want to label that angle theta. So is there any trig ratio that we can think of that includes the adjacent and the hypotenuse? And the answer is, hopefully we can think that it's cosine. Cosine is the adjacent over the hypotenuse. So cosine theta equals X over length B. So I'll multiply both sides by length B and rearrange things. So it says X equals length B cosine theta. Well, from previous section, we have a formula that has the dot product and the cosine. And so I'm going to use that formula, replace the cosine with A dot B divided by length A, length B. And look what happens. Length B's will cancel. And now I know the length of the projection. It is A dot B over length A. Sometimes that length is called the scalar projection, but we'll just keep moving on with this. So I did not find out what that red arrow is, but I did find the length of that red arrow. Now before we move on, this is sort of unrelated, but it's a little related. Can you find a vector of length 7 that has the same direction as A? Well, that's tough to do if you've never done this before, but what you want to do is normalize A. That means divide by its length, so it has length 1, and then multiply that vector by 7. That will give you a vector of length 7 that is the same direction as A. And so there's the expression there. Find a vector of length X with the same direction as A. We kind of do the same thing. We go X times A divided by length A. Well, X happens to be the length of the projection. So I'm going to replace this X right here with this expression, A dot B over length A. So that's what I'm going to do, and it's going to look a little messy. Whoa! So on the top I have A dot B, which gives me a number, a scalar. Then I have a vector A that's to the right of that. And on the bottom I have length A times length A. Now remember, length A is square root of A dot A. So I have square root of A dot A times square root of A dot A, which is just going to give me A dot A. And so there is the formula for the projection of B onto A. Now let's talk about the Gram-Schmidt process. Okay, we're going to let V1 and V2 be a basis for R2. Okay, and they look like that. So what the Gram-Schmidt process is it takes your basis, whatever it might be, and it actually might be a basis that a basis for a subspace within like R7 or whatever, but it's going to be some sort of basis. And what the Gram-Schmidt process does is it does a little wiggling, stretching, a little dance, and then when we're done, we have a nice orthonormal basis that we got from these two vectors. So how are we going to do that? Well, the first thing I'm going to do is I'm going to let one of those vectors be W1, and I'll just let W1 equal V1. But before I do that, I'm also going to point out the projection of V2 onto V1 looks like that. Okay, so you can see that that's the projection. So W1 equals V1, and what W2 is going to be is it's going to be V2 minus this red vector here, projection of V2 onto V1. And what does that look like? That's a vector. I'll use blue to denote it. It's that vector that completes that triangle. Now, since you can move vectors around, I'm going to move that around. I'm going to move that blue vector over there. Now, look at the red vector and the blue vector. The red vector and the blue vector. Okay, so look what we have. They are orthogonal. But what is really orthogonal? V1 is W1, so this is W1 right here, this long black vector. That's orthogonal to the blue vector. They are at a 90-degree angle. And so we got that. They're not orthonormal, but let's normalize them and make them so they're orthonormal. So I've just normalized them, and instead of calling them W1, W2, now the normalized ones are U1, U2. And that gives me an orthonormal set. Now, I know this is kind of weird, and if we went into 3 dimensions, it would be a little hard to see. So what we're going to do is turn this over to the piece of paper, and we'll finish off the lecture there. So here is the Gram-Schmidt process. This is actually written in your definition and theorem sheet. And we have a basis, B, and I'll actually put 3 vectors in this theorem, V1, V2, V3. So on the PowerPoint, we were just looking at 2 vectors. So here's 3 vectors, and that's a basis for an inner product space V. Now here's the thing that your book won't say. Scale your vectors if desired. I will scale my vectors if there's fractions in them. And I'll scale them so there are no fractions in them. Let B prime, now that's not the derivative, it's just another, it's the intermediate step. B prime equal W1, W2, W3, where? So this is the big part of the Gram-Schmidt process. W1 equals V1. And I'll look over here. W2 equals V2 minus projection V2 onto W1. And that is what we derived in the PowerPoint, so that W1 and W2 were orthogonal. Now I believe in the PowerPoint we may have had V1 written there, but V1 was W1. Now, here's where we keep going. W3 equals V3 minus projection V3 onto W1. So we're getting it all squared up. We're getting it orthogonal with that one first, with W1, and then we go minus projection V3 onto W2. So then we are then taking that and getting it orthogonal to W2. But if you look at these three things, W1, W2, and W3, well, W1 is just V1, but W2 is a linear combination of V2 and V1. So obviously it's still going to be in the span of B. So you're just taking a linear combination of two of your basis elements. And then W3 is a linear combination of W1, because this is just a scalar. This is V3 plus a scalar times V1 plus a scalar times W2, but remember W2 is just a linear combination of V1 and V2. So all these things are, especially W2, W3, are just linear combinations of these guys. But we twist this basis by doing this little song and dance into an orthogonal basis. And this is the magic of the Gram-Schmidt process. Then B prime is an orthogonal basis for V. And here's, your book doesn't do this, scale the WIs if desired. Well, yeah, we can scale them all we want. You'll still have an orthogonal basis. And then part 3, B double prime, we'll call U1, U2, U3. We normalize each of those vectors. And then B double prime is an orthonormal basis for V. So remember, orthonormal means it's orthogonal, but all the vectors in that basis would then have length 1, and that's what we have. So sometimes in your homework they'll ask you to stop. They'll say find an orthogonal basis, and they'll ask you to stop after step 2, and sometimes they'll make you find the orthonormal basis, so you'll have to do all 3 steps. So basically we are twisting. We can twist any basis into an orthogonal basis. And that's what we're doing using these linear combinations by this process. So we had Erhard Schmidt. He lived from 1876 to 1959, and Jorgen Peterson Gram, 1850 to 1916. Gram actually died in 1916 after being struck by a bicycle. Okay. Let's go ahead and do one problem. We do one problem. This is what you'll be doing in your homework. Find an orthonormal basis for span S. Okay, so that's what they want us to do. They want it to be orthonormal. So we're going to do all 3 steps of the Gram-Schmidt process. Really, the first step was really nothing, but let's go ahead and do the first step. First step is identifying this as V1, V2, V3. So here's step 1. We're done. Okay. Step 2. We let W1, so I'll write out what's on that definition. W1 equal V1. Okay. So this right here is W1. And you'll always do that. Now, can you make your W1 be any one of these? Yes, you can. I usually just make W1 equal the first one. Okay, the next thing on the definition says this. It says W2 equals. So I'll write out the one that was on the right hand side. It equals V2 minus the projection of V2 onto W1. Okay. So when I teach face-to-face, I actually give this formula and the W3 one with the projection. But since this is an online class, obviously you can look this up and you can look up what the projection is as well, but it's good to know how to write that projection. So here we go. This is V2 minus, okay, the projection looks like this. The projection of V2 onto W1 is going to be the inner product of V2 and W1, and then we have inner product of W1 with itself on the bottom, and then we have W1 here. So notice in the definitions I did not say this, but everything's the inner product because it's a generalization of the dot product. And look, we have a set of vectors and we're not in Rn anymore, we are in M2. So we have inner product. Now we just have to compute this out. So we know W1 is this guy right here. W2 is this guy. To remember this projection formula, I always see that, you have a W1 and a V2. There's only one instance of that V2, and the W1, which is on the bottom, goes on the bottom. And it actually makes, there's 4 of them, and they make a shape like a gun. And that's how I remember that. And then the V2 goes right there. So what is the inner product? It's going to be the standard inner product for 2x2 matrices. So what we want to do is we want to compute this. I'll circle this in yellow. We'll try to color code this. And then this one I'll circle in orange. So we want to figure those out, and I'm going to do the calculations over here. So we have V2 and the inner product with that and W1. Okay, so V2, W1. Here's V2, here's W1. So I'm just going to go ahead and take their inner product by the standard one, where I go 1 times 2 is 2, plus, and then we have another 2 times 1 is 2, plus 0 times 1, 0, and then 1 times 0, 0. So look what I end up getting. I end up getting 4. Also want the inner product of W1 and itself. Okay, so here's W1. I'm going to go 1 times 1, plus 2 times 2, plus 0 times 0, plus 1 times 1. So you know what? That's going to give me, I'll write that out. So 1 plus 4 plus 0 plus 1 gives me a 6. I think I will circle these in their colors. So we'll just make it a little easier. And maybe when you're doing your homework or the exam, you can do the same thing. So let's go ahead and write out what everything is. V2 is this guy right here. 2, 1, 1, 0. Minus the yellow part, which is 4. And then the orange part, 6. Then I have W1, which is 1, 2, 0, 1. So don't you see that this guy right here, W2, is just a linear combination of those guys? But we are doing the linear combination in such a way with the correct scalar that we will end up getting W1 and W2 being orthogonal. See, V1 and V2, when you did their inner product, which is really right here, you got 4. That wasn't 0. So let's continue on this one. I have 2, 1, 1, 0, minus 2/3, 1, 2, 0, 1. So this gives me 2, 1, 1, 0. We have minus 2/3, 4/3, 0, 2/3. So this gives me 2 minus 2/3, which is 6/3 minus 2/3, 4/3. Then this is 1 minus 4/3. This is a negative 1/3. And then a 1 minus 0 is 1. And a 0 minus 2/3 is negative 2/3. So this guy right here is W2. Now, notice what it says on the directions. It says you can scale the WIs if desired. And I do want to scale this. I mean, so your book is not going to do that. I'm going to call this W2 bar with a wiggle underneath it. Okay, I don't even know what that means. So my true W2 is going to be gotten. How could I scale it? I'm going to multiply everything in this matrix by 3. So W2 is going to be 4, negative 1, 3, negative 2. And so there is W2. I'll circle it. And it's really this guy scaled. And it doesn't really matter. I mean, you can use this if you don't feel comfortable with what I did with the squiggle and said, oh, he's going to scale it. But watch what happens when you go W1 and W2. Look at this. You get, I'll do it right here. So W1 and W2, when you take their inner product, it should be 0. So I get 4 minus 2 plus 0 minus 2 plus 0 minus 2, which gives me a 0. So that's great. I have now done some twisting and turning of these guys, wrote a linear combination of those two, and out popped W2, which was that. And now I need to work on this guy right here, which is V3. Before I work on V3, let me show you something that I wanted to do, but I didn't want to lose too many people. So I'll do it in purple. It's when I had this step right here, 2, 1, 1, 0, and then I had the negative 2/3, and then this is 1, 2, 0, 1. So remember over here, and then I went ahead and multiplied the 2/3 through, and then I was like struggling to do my fractions. Another way we could have done this, I'm not saying you have to do it this way, is I could have factored a 1/3 out front. Now when I do that, I have to put a 3 in front of this one. And then over here, this is minus 2 times this one. Okay, so this is 1/3, and then let's see what we have here. We have 6 minus 2, which is 4, and then 3 minus 4, which is negative 1, and then I have 3, and then the 0, so that's a 3, and then a 0, and a minus 2. And so we could have done things, you know, where we factored out a 1/3 on that step. And look what I have. This guy right here, there's a 1/3 in front, is exactly this guy right here. So, you know, if you don't like to to go like 2 minus 2/3 to get the 4/3, and you would rather factor out a 1/3. It's just another way of doing it. So let me just put another way. So I might do that on the third one. I don't know what I'll do. Okay, let's go ahead and figure out what W3 is. So look where we are. We are on step 2. W1 equals V1, so we have that. Maybe I should circle my W's with a certain color. I know I circled that one. I'll just circle them in green. Here's W1, W2. And now what am I going to find? I'm looking at that definition, and I'm going to cover up my W2. I'm looking at my definition, and I see that W3 equals V3 minus projection V3 onto W1 minus projection of V3 onto W2. Okay. So I'm going to rewrite that. Writing out the projections, I have V3 minus, okay, so the projection, you have 4 occurrences of the W1, so I'm going to write the W1 gun. W1, 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 and then W1. So it has that gun formation, and then we put the V3 right here. These are inner products. So hopefully I haven't been saying dot product when I've been doing the inner product. Okay, there's the first one. That's that projection, and the next projection we'll just write out. So this is going to be V3 inner product with W2. Yeah, the W2's on the bottom. So this is a bit tedious. We're not always going to be doing the Gram-Schmidt process in this class. It will come up again. And then here's W2. Okay, so what do we have here? We have lots of stuff. We have a W1 dotted with itself, and that I'll circle in orange. And we have W2 dotted with itself. Okay, so everything else we've got to put on our chart here. So I'm gonna I've run out of room here because I put that. I might just write some things above now. So I need a V3 and a W1. V3 and a W1. So what does that give me? Here's V3. There's W1. So if you do the inner product, you get 1 plus 0 plus 0 plus 1. Okay. 1 plus 0 plus 0 plus 1. I'll write that down. Which is a 2. Let's go ahead and circle that in red. Okay, what else do we need? We need, okay, so we better put this one right here. A V3 inner product with W2. And a V3, no, sorry, a W2 inner product with a W2. So let's see what those guys are. Okay, we'll have to remove that. So here is V3 and W2. So this is going to give me 4 plus 0 plus 6 minus 2. Now what's that going to give me? looks like it's going to give me an 8. Okay, I've got to try to use a color that I have not used. I'll circle this in blue. And then a W2 dotted with itself. This is going to give me 16 plus 1 plus 9 plus 4. 16 plus 1 plus... That's not 16, is it? Okay, so gotta use the whiteout sometime. Where am I? See if it's even working. I was having problems with this. Okay. Okay, there we are. So just bump the tripod. Hopefully the picture's still shining on there. So this is going to be 16 plus 1 plus, so I'm inner producting this with itself, plus 9 plus 4 plus 9 plus 4. That gives me, I think it's about 30. And I'm running out of colors. I don't want to, oh, did I, no, I don't want to use green. Okay, so I definitely don't want to use green, so I'll use brown for this one. So over here, we've got inner product of V3 and W2. Circle that in blue. Inner product of W2 with itself. So this is, once again, this is very tedious. I don't know if it's as tedious as row operations. And let's go ahead and write things up. V3 is this guy right here. 1, 0, 2, 1. Minus red over orange. So that's 2 over 6. And of course, this one's going to be W1, which is 1, 2, 0, 1. And then we have minus blue over brown. So this is 8 over 30. And so this is going to give me what? Then we have a W2 there. Sounds like my phone is ringing. And there's W2, which is 4, -1, 3, -2. So I have 4, -1, 3, -2. So this is my W3. And let's go ahead and simplify those fractions. So this is 1, 0, 2, 1, minus 1/3, 1, 2, 0. And then we have minus 4 over 15. This happens to be 4, -1, 3, -2. Now see what happens? I scaled this W2. Your book wouldn't have, and there would have been lots of ugly fractions in there. Now, remember how I did this little trick where I factored out a fraction? I'm going to do that this time because I don't want to work with fractions too much more, so I'm going to factor out a 1 over 15. 1 over 15, and so that's going to give me a 15 times the first matrix. 1, 0, 2, 1. Then I'm going to have minus, okay, so 1/15 factored out of there, so we have a 5. And then notice you can multiply it back through. 5 times 1 over 15 is 1/3. 1, 2, 0, 1. And then this one's just going to be a minus 4. 4, -1, 3, -2. So what do we have here? We have 1 over 15, and I'm thinking we can just finish this up now. Look at this. This is going to be 15 minus 5, or maybe we shouldn't. Okay, so that's 15. I'll do it over here. 15 minus 5, and then minus 16. So what that looks like it gives me is a -6. Okay. And then this one gives me a 0. negative 10. So I don't have a calculator here, so, and then we have what? Plus 4. So this gives me a negative 6. And then on the bottom I have 30. That's a 0. And minus 12. So 30 minus 12, I think that's 18. And then the last one is 15. Minus 5 plus 8. So this looks like it's 18 again. So this is what, I'll put a little squiggle under here. So this is what W3, the vector W3 with a squiggle underneath is. And we can scale this to whatever we want it to be. So I could actually factor out a 6. And so, you know what? My W3 is then going to be negative 1, negative 1, 3, 3. And it could be really any multiple of this. It's not going to lose its orthogonality with the others. So we have W3. Okay, I think I'm going to need another piece of paper. So remember when we did this, this was step 2. Now we have, I'll just write them down to summarize. W1 is 1, 2, 0, 1. W2 is, it's the one down there, 4, negative 1, 3, negative 2. Make sure I copied it correctly. And then W3 is the one we just found, which is right there. Negative 1. Now, if you want it, you could have written W3 as 1, 1, negative 3, negative 3, if that made you happier. These are the ones that I circled in green. Now, the cool thing about W3 is it should be orthogonal to W1 and W2. Let's just check that. We won't write it down, but watch this. You should get 0. Negative 1 minus 2, so that you're at negative 3, and then we have 0 plus 3. So W3 and W1 are orthogonal, and then watch this. Negative 4 plus 1, so now we're at negative 3, plus 9, so we're at positive 6, minus 6, which gives me 0. So W1, W2, W3 is an orthogonal set. We shouldn't be that surprised because that is what the Gram-Schmidt process guarantees. So in your homework, if they said find an orthogonal set, if they had said the problem find an orthogonal basis for span S, you'd be done. You'd have to put these in braces and list them, and then you'd be done. But they said find an orthonormal basis. So now I'm going to do part 3, where I should take each of these and divide them by their length. So let's just go ahead and, maybe in blue I'll put the length. What is the length of that? Well, I take the inner product of this and itself. So this is going to be 1 plus, and we actually already did W1, that's 6. The length is not 6 for that one. The length is square root 6. And the length on this is W2, inner product of W2 with itself. I think this is right up here, which is 30. So we're going to say root 30. And then the length of this guy right here is 9 plus 9 is 18, 19, 20. So root 20, which is really what? That is 2 root 5. So those are the lengths. So step 3 really isn't that bad. Step 3 says, let's just go ahead and write out the answer now. Your U1, U2, and U3 look like this. So 1 over root 6, I'm normalizing this vector. 1, 2, 0, 1, comma, 1 over root 30 times this vector, 4, negative 1, 3, negative 2. And then the last one, I'll normalize this guy, and I should use the simplified square root. This is 1 over 2 root 5. And then we have negative 1, 3, 3. And in terms of the theorem that we had up there, there was a U1, U2, U3. I mean, this guy right here is just U1. You don't have to write this U2, U3. And remember how I scaled down W3? I could have actually made W3 have fractions in it. Well, if I had done W3 with fractions, by the time I normalized it, which would have been kind of a nightmare, I would have ended up getting exactly that vector. Okay, because these guys have the same direction, they just have different lengths. And then this is the one that has length 1. And each of these have length 1. So I have an orthonormal basis. This is what you'll be doing in your homework. The Gram-Schmidt process is a little tedious. Just keep the inner products like on the side, have a table of them, so then that way when you do this step right here, you can just get them from the table, and even if you color code them, that makes it simpler. And then try to avoid the fractions. That's what I do, and that's why I factored out a 1 over 15. Of course, I had to work with bigger numbers like 30 and 8, but I didn't have to work with fractions. And if you look at the solutions manual, the student solutions manual, if you have one, there's going to be fractions all over the place. You're going to go, what is this? So I try to avoid the fractions. So that is the answer to the problem we're doing, and all the problems are kind of like that. I think in your homework you have to Gram-Schmidt. Sometimes there's only 2 vectors to Gram-Schmidt, and that's going to be a lot nicer because then you don't even have to do the W3. You just do W1, W2. Well, that completes section 5.3. Do your homework. Have a good day. I'll see you on the next video.